We have just finished a section on atomic structure and the location of the electrons within an atom. So we want to begin to put those atoms together and actually create molecules. So we need to start talking about chemical bonding. As you can see on the screen here, we have a variety of molecules, and hopefully by going through chemical bonding we'll be able to answer several questions. We will be able to determine how is a molecule or polyatomic ion held together, why are atoms distributed at such strange angles. So we're going to take a look at the 3D structure of molecules and actually try to draw them three-dimensionally. Why are molecules not flat? And then what kind of properties do these 3D structures then give these molecules? Can we predict the 3D structure of the molecules? And then how do those particular structures give those molecules certain chemical and physical properties? In order to do this, we need to review the different types of chemical bonds. Basically, there are three forms of bonding. The first type of bonding is ionic bonding. We have studied this one. We've taken oppositely charged ions and put them together in the right ratio so that their total charge is equal to 0. So we're putting oppositely charged ions together. The second type of bonding is what we're going to work with here pretty much throughout this unit, and that is covalent bonding. This is where the electrons are actually shared between two atoms. They're not completely transferred as in ionic bonding. And then finally, metallic bonding is what holds the atoms of a particular metal together. And we will briefly discuss metallic bonding, but the bulk of the time here will be spent on covalent bonding. So let's just take a brief look at ionic bonding. Ionic bonding, as I said before, are the positive and negative ions coming together. And what you form basically in a solid ionic compound is the crystal lattice that you see on the screen there, the green and the red pieces held together. Ionic compounds, therefore, are usually between metals and nonmetals because we're looking at oppositely charged particles. So an element from the left side of the table combines typically with an element from the right side of the table. Now, we will begin to draw covalently bonded compounds, and to draw covalently bonded compounds we're going to use something called a Lewis structure. And this Lewis structure will actually help us to determine how many atoms will combine. Now with ionic bonds, we took the charges of the two opposite ions, we put the elements together, tried to get the total charge to be 0, and from that we could get the subscripts. With covalently bonded molecules, rather than using charges, we actually draw these Lewis structures, and from that we can determine the formula. In order to do that, we must understand what valence electrons are. So a quick little review here. Valence electrons are the outermost electrons. They are distributed around the molecules as either bonded pairs, okay, so they're participating in a bond, or they're there as a lone pair, so they're sitting there on that element, but they're not necessarily participating in a bond. Now, when a bond forms, you actually get orbitals overlapping. So in this HCl molecule, you'll get the orbital of Cl overlapping with the orbital of the hydrogen, and then the electrons that are in the bond then occupy that space that's overlapping there, as seen in this picture. Now, again, valence electrons, we need to talk about what those are. Remember that the outermost energy level contains electrons, and we're looking at just the s and the p electrons in that outermost energy level, so we kind of ignore the d electrons there. So if we look at boron, for example, the electron configuration is 1s2, 2s2, 2p1. The outer energy level is the second energy level, and there are 2 electrons in the 2s, 1 electron in the 2p. Add those two together and we get 3 valence electrons. And then notice we've taken the symbol boron and we've put 3 dots. Each dot symbolizes one of those valence electrons. Let's take a look at bromine. Bromine's configuration is argon core, 4s2, 3d10, 4p5. So the outermost energy level there is the fourth energy level. And again, we take the s and or the p electrons there, 2 electrons in the 4s, 5 electrons in the 4p, add the 5 and the 2 together, and bromine should have 7 valence electrons. So therefore in the dot diagram you see 7 dots around the bromine. Now, a real quick and easy way to determine valence electrons is to simply look at the group number that the element is in. So for example, hydrogen is in group 1, so it's got 1 valence electron. Beryllium is in group 2, so therefore it has 2 valence electrons. If we go all the way over there to boron, boron is in group 3, so it has 3 valence electrons. Carbon in group 4, nitrogen in group 5, oxygen in group 6, fluorine in group 7, and then finally the noble gases are in group 8. Now helium is kind of an exception. It's in group 8, but it actually has 2 valence electrons.